Good morning, ladies and gentlemen. It's a real pleasure for Anne and me to be here, and we hope, of course, that we can help you, assist you also with this topic of the concrete roundabouts. So I think we will first start with presenting ourselves.
So I'm Anne Beeldens. I'm almost 1.5 year independent consultant in concrete pavements, so from the design to execution to follow-up to some problems which may occur. Before I worked at the Belgian Road Research Center for 14 years, and I'm also teaching, I think 15 years now, at the University of Leuven at the Department of Construction.
So my name is Rens. I work now for over 17 years for the Belgian Cement Association, which is called FIBELCEM. And my job there is consulting engineer. So also, like what I'm doing today, it's also assisting designers, road authorities, contractors, and whoever to build good concrete pavements. Since 2009, I am also managing director of EUPAVE. EUPAVE is the European Concrete Paving Association, of which the Slovenian Concrete Association is now a partner. So we're very happy about that. And so that's also why it's a pleasure for us to be here today. We'll have a joint presentation, so we'll switch from time to time. We'll try
if
not
you
to
get bored
fight.
of one, you switch to the other. So I will start with some small introduction, why roundabouts and especially why concrete roundabouts. Perhaps before, just tell you that in Belgium we have a lot of experience in concrete roads. We have roads who are 70, 80 years old. Our highways are for 40% in concrete, and they're over 40 years old without major problems and major maintenance. So they're doing very well. Since the 90s, we're starting to have roundabouts in Belgium. Before, I think they only had them in Great Britain. But now, the 90s, they came to Belgium. And very soon, we start to build them in concrete, because we saw that it was really important to have a durable roundabout. And there's some differences with a normal road. The roundabout has different stresses. So why roundabouts? I think mainly because their speed reduction. So for safety reasons, also in some circumstances they can be very fluent. You don't have any lights anymore. You can kind of make that people go through very fluently. And again, for safety, you don't have any accidents, frontal accidents anymore. I think that's one of the main reasons. One important thing in Belgium is this little sign. This means you have a roundabout. And sometimes in the cities we saw that they just put something in the middle, they put this sign, and then they had a roundabout. Very quickly that was changed, because you have all those forces going on that roundabout, even with small traffic. And so they really put the roundabout in place. Geometric design I will not enter. I will just tell you the main parts. You have to be sure that your traffic goes fluently, so you have to look at the 3 ways they can go. To the right, continuous, or to the left. It depends how much traffic you have on those 3 directions, how your roundabout has to be designed for capacity. You also have to make sure that the trucks can pass. I found in the US Department of Transportation, they say you need at least 1.5 meters between your sideway and your main axe. In that kind of turn, and 1 meter here in the middle. So then you know your radius, and then you know what speed people will normally take on that roundabout. Does not mean they will not go faster, but that's the main speed you're designed for. You also have to take care of the vehicle size. If you have really big trucks who have to pass, you need a lot of space. You need to make sure it's wide enough, or you need to take special precautions. Sometimes there is a go-through for the special traffic, the very large trucks, which is not normally open, but can be open if a large truck has to pass. Now coming to traffic loading on a roundabout, you see, because of the centrifugal forces, that the truck is going on one side, so you have instead of dividing the axle load, which is 13 ton in Belgium, maximum axle load, under two wheels, one wheel will get much more, and so you will have much more stresses in your outer ring of your roundabout. Which means, of course, that this part is very used, and you need to design it properly, so your traffic there will double almost if you count that overloading on the wheel side. Same view here. You see the truck is really going on his outer wheel. All those stresses are coming there. The inner section is less used, but for trucks, even this part, where normally you cannot drive over, we call it the rubble part, which makes a lot of noise to avoid that cars go through, but it's there because of those trucks can go over it. So in Belgium, we make both parts in concrete to be sure that it withstands the trucks. What are the consequences if you don't do it in concrete? So I think if you do it in asphalt, these are some views of asphalt roundabouts. Some are good, but they don't last that long. You have rotting, you have delamination, you have loss of surface aggregate. Not only because of the forces, but I have a particular case in Belgium, which was just across the France border. And in France, the prices of the diesel were very high. So what happened? All the trucks who came by Calais, going to wherever, Germany, Belgium, Holland, whatever, they drove just the moment they arrived in Belgium, so they went off the highway and they went to a little gas station, which was a bit further because the price of the gasoline was much lower. And then they came back, they took the roundabout, and because they were so filled with diesel, with gasoline, all the diesel was spilled. So after some months, really the asphalt was eaten away because it didn't resist the oil. So it was just eaten away because of the turning in the roundabout. So if you have a gasoline station nearby and it has low prices, especially then take the concrete. That will resist the oil without problem. Perhaps you can even gain some diesel at the site, who knows. But so it's not only the rotting, but it can also be the spoiling of material of diesel from the trucks especially. So the roundabout is really solicited. With the concrete, you can design for it. You can make the choice that it will last for 30, 40, 50 years. But it's not only the roundabout. Of course, you have to come to the roundabout. A roundabout is made to slow down. So you will brake when you're getting to the roundabout. So also the approach legs have to be taken care of. Because what are you doing? You're not only braking, you're also waiting. And when a heavy truck is waiting on the asphalt, there will be some rotting. So the approach legs, we will talk about that later in the presentation. But so you have the reducing of speed, you have the braking, and you have the waiting area. Also that area, I think, should be in concrete. If you don't do that, you will see very fast rotting appearing in that area. If you take the legs with the roundabout, then you will have a good solution which will last a very long time. So why then the choice of concrete? Of course, it's a very durable material. We see in Belgium, we have roads 75, 80 years old without a lot of maintenance. We just fill the joints, and if they stay filled up every 10 years, something like that, so change the joint filling, then your road will last, let's say, almost forever, or even for sure for a lifetime. So we design for 30 years. We see that mostly they last for 50 years. Our highways are now a lot 40 years old or even a bit older, and they're still in good shape. The maintenance is reduced. If you have the slabs, you need to take care of your joints. If you have roundabouts, for example, in CRCP, maintenance is even lower. One says that the concrete is more expensive when you place it, but when you look at it over a long time, you will see it becomes very economically because it will last for a long time with a low maintenance, so then the cost will be reduced very, very good, and it will be a good choice for long-term investment. It's a light-colored surface. which helps to get less heat from that surface. It's also very visible. It is good when it rains. The water can go away quite easily. And when you use the good aggregates at the surface, you have a very durable skid resistance. You also can give it some color. You can play with colors, which makes it an aesthetic appearance. You can give it some extra value in your city. But concrete has also a but. You have to place it correctly. Once concrete is placed, it's very difficult to repair. So if you do it well, it will last for a long time without any problem. So that's why we're here, I think, to show you how we do it and to hope that you take the same measures and to build the same good, durable concrete. So now I give the word to Luc.
Thank you. So basically, as most of you will know, there are two main types of concrete pavements, which are the slabs, which we call the jointed plain concrete pavements, either the continuously reinforced concrete pavements for the slabs characterized by the joints, transverse joints, while the continuously reinforced concrete, CRCP, is characterized by the absence of transverse joints, so no joints. We have roundabouts in both solutions. I will start with the first one, so in the jointed plain concrete pavement. And I also say a word about reinforcement and a joint layout. So, as a roundabout is a special circular part of a road, now we see that the transverse joints are now the radial lines, so the radial joints. But the type of joints can be the same as for a normal pavement. So you have the joints that we cut, which become transverse or now radial contraction joints, which allow the shrinkage, contraction of the concrete pavements, which also allow for a bending between the slabs. In some cases, you can have expansion joints, where you allow the concrete to expand under in case of increased temperature. Normally, we will never have an expansion joint on the roundabout itself, but we can have it in the approach legs. A construction joint is what we call a joint when we interrupt the construction of the pavement. So when you stop and you continue the next day. Besides the transverse, we also have the typical longitudinal joints. In this case, they are the circumferential joints. And here too, you can have a saw cut, and then it becomes mainly a bending joint. Also a little bit contraction, but that is less important due to the limited width. You can also have a construction joint if you make two circular lanes next to each other. And in some cases, an isolation or a separation joint. I'll come back later to that special type of joint. And yeah, as you can see here on the screen, here you have it's a good view because you can see very well. So the transverse radial joints. Here a saw cut, a longitudinal bending joint, and in this case a longitudinal construction joint, which you can see due to the different color of the concrete that was used. So we have different types. I told you, normally we talk about a jointed plain concrete, which is unreinforced. And indeed, a normal concrete pavement, concrete slabs, normally do not need any reinforcement on the condition of having a good substructure, a good base layer. Why we don't need any reinforcement? It is because, after all, a good quality concrete has a good bending strength. So it goes, it's a flexural strength of the concrete, which can go up to 4, 5, 6, and even 7 megapascal, which is enough to withstand the stresses induced by the traffic in the lower part of the slab. So normally you don't need any reinforcement. But in some cases, anyhow, we do want to put a reinforcement. That can then, you see the 3 types. You can have a steel mesh, or you can have steel fibers, or nowadays you also see the appearance of even structural synthetic fibers. And for all those 4 cases, you can combine it with the use of dowels. So for all 4, it can be a doweled concrete or undoweled. A few pictures which are, some of them are for roundabouts, some of them are just for a pavement. As you can see, transfer radial joints are made by saw cutting with the adequate equipment, smaller equipment or a heavier one for the longitudinal. You see this is a longitudinal circumferential joint of a roundabout. You see that we have to saw cut up to 1/3 of the thickness, and that then we have a good crack inducer, and that a crack will appear mostly during the first nights because of the drop of temperature during the night and the stresses it creates. And after all, after finishing and filling the joints, you get a nice appearance. So I said that we could use or not use dowels. What are dowels? Dowels are steel bars, smooth steel bars, which are covered with a coating which has 2 functions. One of the functions is to prevent the bond between the concrete and the steel, because we put the dowels in a transverse contraction joint, so the pavement, the joint, should still allow the movement, the contraction of the concrete. And the second function of that coating is corrosion protection. What is the main purpose of the dowel? Well, it is the load transfer from one slab to another, which is presented in those 2 figures, which are both theoretical cases, because this is a theoretical case of a 0 load transfer for a load approaching the joint. You see that the loaded slab is deflected, not the unloaded. In this case, you see it's a theoretical case of 100% load transfer, where you can see the same deflection for the loaded and the unloaded slab. So that is why we need dowels for. And that is only necessary in the case of heavy traffic and intense and heavy traffic. Now, if we choose concrete for a roundabout, mostly it is because there is a lot of traffic and there is a lot of heavy traffic. So normally, in most cases, for roundabouts and concrete slabs, you should use dowels. Dowels also play a role in thickness design, which is, let's say, a bit the theory when you're going to calculate the stresses and the thickness of the concrete you need. You can see for a doweled pavement compared to an undoweled, you can reduce thickness from 1 to 2.5 centimeters. Or you can not reduce, keep the same thickness, and of course have an extended lifetime of the pavement. Important in practice is that the dowels have a correct and a stable position, so that dowel baskets are fixed very well to the base layer. Therefore, it's also good to have an interlayer of asphalt, which makes it easy to connect the dowel baskets to that support. Or in some cases, you can use a dowel bar inserted on, which is installed on a slip-form paver. So, as I said, normally the reinforcement, the steel meshes are not necessary. However, it can be convenient, because if you put some steel meshes, well, it allows you to eventually reduce the thickness, maybe 1 or 2 centimeters less. Or you could increase the slab length, or you can use slabs of an irregular shape. I say or because it's not because you just put one mesh that you can and reduce thickness and make them a lot longer in the same time. A typical solution for the use of meshes is the diameter 10 millimeter spaced 150 millimeter. It's still, for those who have to do it, feasible to do this by hand. It's not too difficult. Normally we place them in the upper part of the slab because mostly it is used as a shrinkage compensating reinforcement and not really to take up the bending stresses. And in that case, we recommend a minimum cover of 50 millimeters. Again, we have slabs and contraction joints. So those joints must be able to do their job, to function, so to open. It means that the presence of the steel reinforcement through the joint is not a good idea because that will hinder the movement of the joint. That is when you're going to cut the joints that you also have to cut through that steel mesh. Now, at least if it's in the upper part. It's less important for a mesh situated in the bottom part of the slabs. The mesh can be combined with dowels. Well, you see a practical example here on the right and the layout on the left. And what we do recommend is to have some overlap of the mesh and the dowels, because we had some case where the mesh stopped here and it still induced a crack, possibly to the different stresses. Yeah. So it's safer to do it this way. You can also use steel fibers. You know, in Belgium we have the company, well-known Bekaert, which produces those steel fibers. So around their production plant, we found roundabouts in steel fiber reinforced concrete. Later on, I show an example also in Australia. They're very fond of the steel fiber reinforced concrete. Well, it has some advantages. You don't have to place your meshes. Maybe it can go faster. But let's say the basic principles are the same, which means that normally you don't need them. But they give you some extra benefits. And in the case of the steel fibers, they have enhanced a better post-cracking behavior. So if there's a crack, well, it remains somehow better closed. There's an increased flexural strength, and not really important for roundabouts. You also have a better impact resistance. Typical solution is from 30 to 50 kilograms per cubic meter. I think 30 is a good. But it also depends on the size and the type of the fibers, because at Bekaert they also continue to develop their products, and now they have developed some better angled with special hooks on the fibers, which allows lower dosages. On the other hand, also be aware that the use of those fibers will possibly influence the workability of the concrete. So it will become, and also slightly may influence the concrete mix. It's possible that you will need maybe a bit of more fine sand to have a good mortar around the steel fibers. So steel fibers, we do not have a lot of them in Belgium, but there are a few. And we even have one example, I think, with synthetic fibers. With synthetic fibers, be aware, I'm not talking about the very fine, small-sized polypropylene fibers, which are mainly used for compensating the plastic shrinkage. Here I'm talking about the larger sized structural synthetic fibers, which can replace the steel mesh or the steel fibers with doses from 4 to 6 kilograms per cubic meter. Here also the quality, the shape plays a role, and also the workability is influenced. It is not easy to compare the steel and the synthetic fibers, and I do not believe everything what is in the commercial pages of the synthetic. But we can use it, and you see that this is an example of a small, nice roundabout. You see a joint, it was in jointed slabs. I think it was maybe initially provided in CRCP, I don't know. But you see they added the fibers, and you can see here a picture, and you see some of the white-colored synthetic fibers coming out, which is not a problem because you really have to look for them. It's not on some places at the edge, because at the central part you don't see them anymore. So important for the slabs is the position of the joints. So here you see the easy way where they simply pave through. It's it's, let's say here you create the roundabout with the road markings. Those are examples coming from Australian guidelines, which were edited in 1996. So the Australians were quite. Here you also see, this is an example what they had of a typical design, what they say, for a steel fiber reinforced concrete pavement. And you see with a lot of approach legs. So, but I tell you more about how we see it, how to do the joint layout. First of all, I just remind you of some basic rules. Basic rules which are not typical for roundabouts, but just for the concrete pavements, the concrete slabs. So there is a maximum length to respect. In Belgium we say don't make it larger than the joint spacing than 5 meters. Here I say, okay, if it's a thick pavement, 25, you can go up to 6. Between 20 and 25, keep it to 5. And from, let's say, 18 to 20, make it 4.5. So those are good rules. Also the slab width. How wide can you make it? You say if you can make it 5 long, we can make it 5 wide. Yes, you can. Our rule in Belgium is 4.5. It also corresponds to what the colleagues in the United States say. So it's 4.5 meter wide is a good approach. And that is mostly, it's not that much related to the shrinkage or the thermal contraction of the concrete. No, it's more related to the effect of the curling and the warping, which is caused by the difference in temperature on the top and the bottom of the concrete slab. So the temperature gradient, which causes a slab to curl upwards or downwards. And with the danger, the effect, if you make your slabs too wide, that under traffic you risk to have a longitudinal crack. And in practice we see that. It's also good to keep the slabs in somehow square shape. So don't make them too long and too narrow. No, make it as square as possible. Well, how much? Well, I say a length-width ratio, if possible, limited to 1.5, but 1.75 is also good. It's not a strict rule, but it's a good recommendation. And the angles, so the joint angles, well, if they can be 90 degrees or more, that's okay. If it's a sharp angle, acute angle, then it becomes dangerous because you get a concentration of stresses and possibly a crack initiation. So we say, okay, keep them larger than 75 degrees. Now, okay, you can say, well, those are a lot of rules. Do I really have to respect it? Why shouldn't I make it 6.5 or 5 meters? That's also possible. Yes, everything is possible. What I tell you are strict, quite maybe conservative rules. Yes, but those conservative rules give you a very high probability of success right on the after the start of the construction, but also on the long term, also based on experience. Of course, we are talking about heavy traffic pavements. If you really want to make a pedestrian path in a park, you don't have to respect all those rules all the time. So, but with those rules, so I say you have a low probability of early or long-term damage, even under heavy traffic. Now, if you really have a problem with following those rules, so I really want to make it 7 meters, okay, but then I come back to my reinforcement. I say, well, in this case, it can be interesting to put the reinforcement because, as I said, with reinforcement, either the steel mesh or the steel fibers, it is allowed to make it a bit longer or a bit wider. So it's a very easy solution, and mainly so reinforcement is used for that purposes. So now we go more into detail about the positioning of the joint. So with a special attention for both the roundabout itself, the circular ring, and the approach legs. And we have two types of solutions, the A and B. And A says the radial joints of the roundabout should match with the longitudinal joints of the approach legs. So it is one continuous joint. So the joints are matching. Or solution B is we don't care about it and they are not matched, but we isolate the circular ring from the approach legs. So two different solutions, and I put some countries, like solution A is mainly in Austria and Belgium, the United States. Solution B we found in Australia, Switzerland, Germany, France. So this is not strictly, but it is what I mostly found. First solution A, where the joints have to match. Well, it requires more attention. You have to think a bit more in the design and the construction phase. But it has the advantage that you can connect, in this case with tie bars, the roundabout and the approach leg. And so this is a typical layout of such a roundabout. You can see here in blue, you have the doweled contraction joints. And you see that the spacing of the slabs is different. Why? Just because we want those transfer joints to match with either a traffic island, either here a joint. The green ones are free working joints, which we create in order to avoid the sharp angles. And here you see in this approach leg a longitudinal joint, and you see that, okay, it ends and then it becomes the radial joint of the roundabout. So if you want to apply this, it is clear that you have to study this in advance during the design phase, so that you have your joint layout ready, and that during construction the contractor knows exactly what is expected, because once you cut one joint, well, the place of the other one is also determined. So that is important in this case. Yeah, we see also the longitudinal joint, which is a tie joint in this case. In an approach like sometimes you could also imagine that here could be an expansion joint, if this is also concrete. Another example of layout. So it's a little bit the same. Here you see where the joint match, longitudinal joint becomes the radial joint. Here you see another case. Here it would become too narrow, so here the longitudinal joint stops, which means that here we have to maybe put an isolation joint, so to avoid further cracking of this slab. Here you see again the matching of the joints, and we also see that we indicated the slabs where we want to put the reinforcement. Why? Because they are a bit larger than the design rules, or because of the irregular shape, which you also can here see at the enlargement of the road. Here is a good example. It's one of the few examples in the United States. A few years ago, and we were on a visit in Wisconsin, when there are a lot of concrete pavements, a lot of jointed slabs, and they had this one roundabout, and you see the Americans, well, they know how to make their joint layout, and you see that everything goes fine. They avoid the sharp angles. So this is a very good example of the solution A. Then we come to the solution B, where I say that's an easier one in design of construction, because the position of the joint is, let's say, is less delicate. But then, as I said, we have to make an isolation between the circular port, the roundabout, and the approach legs. What is an isolation joint? Well, it is just a separation of the concrete with or without the possibility of expansion, or with a limited possibility. And mostly we use this foamed PE, polyethylene. You see it's this kind of strip. Here you see in some area, you see where we put it between the curbs and a concrete pavement in order to avoid a direct contact. Of course, it has to be cut off afterwards. But you understand, if you put this kind of isolation joint, that it's more difficult also to place the tie bars or eventually dowels between the circular port and the connection. It's possible, but it's more difficult. This is an example of the layout of solution B. And you see the blue line is an isolation joint. But then you see here, in order to avoid the sharp angle, there is a joint that stops, and here there's a joint that stops. You see they do not match. And this is typically what they do in Switzerland. In Switzerland they have quite a number of this type of concrete roundabouts. And you see you have a very good view on the joints here. And you see this is then the isolation joint, and here you have this joint that stops here in the middle, so which is not continued. Now, is it necessary to connect the two ports? Well, it is the better solution. I have observed in cases where they did not connect it, that you simply had an opening of the joint, and in some cases, yeah, it can be up to 10 millimeters of opening, and that is always detrimental. It's a bad solution on the long term. Yeah, another example from Switzerland. Again, here where you see that the joints do not really match, but you see those are still, yeah, very nice achievements. So very good constructions. An example from Germany. In Germany, they build a lot of concrete motorways, but not that much roundabouts. But they started with one, and they also used that solution of the isolation joint. You see, I indicated them here. So the joint that stops. And yeah, another disadvantage of not connecting the approach legs to the roundabout is the fact that you don't have any load transfer. Well, the Germans have another solution for that, and they use a concrete beam beneath that joint. The concrete beam prevents the deflection of the pavement, so it ensures a better load transfer, yes. But as I said, you still have the problem of a possible shrinkage of the concrete and the joint that gets opened. Some attention points also for all kind of pavements, especially for the roundabouts also, but mostly in roundabouts we don't have manholes or gullies, so that's easier. But maybe in the approach legs, and then it's good to provide some extra reinforcement. Those are also examples I got from Switzerland. Or it's also possible to make a contraction joint going through the manhole. That's another solution. Avoid the acute angle. You see, this is an example in Belgium where we did not take care of it, and there's already a little crack. You see, it's difficult to prevent it from cracking. So what we do normally, this small triangle we concrete together with the roundabout, as you can see here. I come back later to that during the construction. This is most of it what I wanted to tell about the jointed plain concrete pavements, and Anne will continue with the continuously reinforced.
So, as Luc told you, you have two solutions to take care of the shrinkage. You can reduce your slab length, or you can say, no, I just keep it continued and I put a reinforcement in it. And that's what you do with CRCP. You put a longitudinal reinforcement in it. You make sure in normal concrete road you make sure that it's kept on place at the ends. So we make lugs at the ends. But in between, it just keeps on going. What happens with the concrete? It cracks. It cracks freely. We now put induced cracking, so we have cracks every 1.20 meter approximately. But so you will have cracks who can occur wherever. We want them with a certain pace, let's say 1 meter to 2 meter interdistance. And the cracks are so fine that no water will go in. So with the reinforcement, the cracks will be closed. And you will end up with a concrete pavement, which is cracked, but which is very durable because the cracks are so fine, so close that no water will go in. The big advantage is that you don't have any maintenance. The cost is a bit higher, but it can resist very well traffic, and it will have no maintenance at all because it doesn't have any transfer joints. You only have a longitudinal joint which you have to maintain, but that's the only thing. So one of your colleagues from the Walloon road authorities had the idea, why not do it on a roundabout? Because you have the reinforcement, so your roundabout will resist more to traffic. But with the reinforcement, you don't need those transfer joints. And as Luc explained, it's very difficult to make them correctly to avoid any extra cracking. So for the large roundabouts, because you cannot bend the steel very short, so when you have a large roundabout, most of the time it's in industrial zones where you have a lot of heavy traffic, CRCP, so the continuous reinforced concrete pavement, is a very good solution. Why? In the case of a roundabout, you connect the reinforcement to itself. So you don't need any lugs at the end. You just connect the reinforcement and you have your continuous reinforcement. So you see some examples. You see again, all the examples you will see with CRCP, they're very large radius, meant for heavy traffic. What are the advantages? So you don't have any joints. You can have a longitudinal circular joint, but no transfer joints. So it behaves on itself. So you connect it very easily also to the roads adjacent. And you have some extra reinforcement for the trucks who are giving those extra forces. So normally we use steel for CRCP, which has a diameter of 20 millimeter. In the case of a roundabout, of course, you need to bend it. So to be able to bend it, we reduce the diameter to 16 millimeter. As I told you, you don't need those anchoring abutments at the end, so you don't need to take care of any special measures to keep the reinforcement in place, to keep everything in place. You just connect them to one to the other so that you have a continuous reinforcement. For the CRCP on highways, for example, we use steel reinforcement, longitudinal steel reinforcement of 0.75%. To be sure you know where it is in the upper part of the pavement. So we put it at 8 centimeter, so 80 millimeter from the top, more or less, to take especially shrinkage, thermal stresses, to take them into account. So for the roundabouts, we reduce a bit the reinforcement rate because we have also the transverse reinforcement who plays their role. So we say 0.67% is sufficient. And then you come to the layout you see here. So when your roundabout is, for example, 23 centimeter, you use 16 millimeter as the longitudinal reinforcement, 40 millimeter as transferred reinforcement, and you put 130 millimeter spacing between the reinforcements. Of course, I just go further. When you see it, when you go further, so here you have the longitudinal, the transverse. The further you go, the wider the transverse will be, so you need to take that into account. As I told you, you put it at 80 millimeter from the top, so it needs to be in the upper part to be able to close those cracks which will be formed. And be sure you will have cracks, but you will see that those cracks are very fine. They have to be there. If they're not there, you have a problem. So they have to be there, but they will they don't form a problem for durability. So I told you, you have to connect the longitudinal reinforcement. Don't do it at one special radial line, so at one line. Make sure that there is a, so no concentration, that it is, so I have to look because it's not easy to see. It was easier on the, I think you see them here. But in any case, so don't make them like this, but make sure that you have a certain angle where you make the connection between the different longitudinal reinforcements. So here too, you see that here, you see lines where the reinforcement is connected, the longitudinal reinforcement. So make sure they're not in one radial line, but that they're divided over a certain area. So I told you, when you have your longitudinal reinforcement there, your transfer reinforcement, we still put it at an angle of 60 degrees. Some countries, they put it straight. They put it at an angle of 90, just like this. We put it on an angle of 60 degrees. They help in closing the crack, which is normally formed radial. So it's an extra help. And you avoid that when there is a crack, it's directly above transverse reinforcement. So that's why we put the 60 degrees. Very rarely we see that a crack is formed and is following those transverse reinforcement, but that's no problem at all. But mainly they go straight radial. If you put the longitudinal reinforcement, of course, here you have a small spacing. There the spacing is much larger. So you don't have the same rate at the outer radius as at the inner radius. Therefore, we put an extra reinforcement here. So over a certain length, mainly half of the roundabout, we put the reinforcement. Again, you cannot have the transition to reinforcement bars to 1 at all the same radius. So what we do, you see here, we just cut them in different lengths. It's not very clear, but here you see it more clearly. We make a kind of angle so you don't have the transition at one radius. If you have that transition at one radius, you will have a drop in stresses or a gain in stresses. So stresses, you will have a difference in stresses, which can cause a crack, which can cause a problem. So that's why we do it in that way. So that's for the large roundabouts, but of course, when you put a CRCP roundabout, normally you have a lot of heavy traffic. It is a large roundabout, so you will mostly foresee 2 lanes, and then you will need the extra reinforcement. So once more, a view on the roundabout. So you see here the chairs, which are placed radial. On those chairs, you put the longitudinal reinforcement, and here you see very well the line. It's not straight, not radial, but you do it on a certain angle. And then you have your transverse extra reinforcement put in place with here the difference in length of those extra bars at the outer radius of the roundabout. We also always put it on an asphalt interlayer. So for that roundabout, we use a lean concrete base layer. We put 5 centimeters of asphalt on top of it, and that makes that you have a very smooth surface where you can place your reinforcement on it. If you do it directly on the lean concrete, it's much more difficult to place them correctly. And the asphalt is also giving you a bond. The Americans call it a debonding layer. We call it a bonding layer because it bonds to the concrete, so to the lean concrete beneath it and to the concrete pavement above it, which makes a transverse of stresses, which is good for your lifetime of your concrete. So it will help. It will disappear after some years. I just had the experience, so after I think 30 years of being in place of a highway with limited amount of traffic, but there we found that like 30–40% of the bonds were still there. The others were lost or at the lean concrete interface or at the pavement. But so after 30 years, you still have some bonding, which helps in the transfers of the stresses. So CRCP is for the large roundabouts, but of course you have to connect them. And there you have also heavy traffic, so make sure that your connection is well done. I would say there, for sure, you have to make your entry legs with concrete, because otherwise you will have problems of rutting almost immediately. This is an example. So here, of course, the CRCP, you don't need any joints. You have one joint, one transverse joint, because you have to start and you have to end. You can have one, you can have two, if you do it in two phases. For example, if traffic needs to go over it during construction, you will have to do it in two phases. But so make that, like here, the transverse joints are at a good place, that they don't cause any problem with your entry legs. And then you just have the same principles, so avoid all acute angles. So these parts are put in place at the same time with the CRCP. Luke will tell you further how you do that with the slip-form paver and some manual work. And then you just connect, so this will be reinforced, and then you go further with your concrete pavement, the length you want it to have. So CRCP roundabouts are a bit more complicated, I would say, in construction. You need to have the reinforcement. But in design, it's quite simple. You don't need to take care of all the joints. And especially if you have heavy traffic, if you have a large roundabout, so for really to get a lot of trucks on it, it's really a good solution which will last very long. We have them since '96 and they're still in very good shape. So I give back the word to Luke, who will tell you about the construction aspects.
Yes, well, I think now that of all, we have a few hundred roundabouts in concrete, I guess, in Belgium, and I would estimate that 80 to 90% is in CRCP. Once we started it, almost all of them are CRCP. We only have a few in slabs. The construction aspects are mainly the same for both. I will explain you the manual and the mechanical paving. Manual between fixed formworks, well, that's the fixed formworks, that can be the curbs or the gutters that have been installed, or the formwork like some wooden beams. Here you see how they can be connected to keep the same height. Formwork that must be in a stable position, either by putting stakes or by a stabilized sand that is used. Here they even put some connection bars, but that's maybe just a little bit exaggerated. It's just only possible if you keep the formwork in place afterwards. You also have, okay, you can do it with wood, but then you have to try to follow the circular shape. But there also exists some flexible formwork materials, like this flexible polyethylene tubes, which allow to follow exact the curvature. And you see also with a lot of stakes drilled in the ground to have a stable position of them. For manual construction, we do the compaction by poker vibrators and a vibrating screed. Poker vibrators, not just one, but you see one per about 2 meters of width. Here you see all the material which is ready in place. Spreading of the concrete by the cranes in front of the vibrating screed. And here you see the people who start with the pre-compaction with the poker vibrators, and then the screed that is following afterwards. Here you see then the vibrating screed. And you see this is the use of a kind of ski which follows the concrete curb that is in place. You see most of the examples we show are for construction of CRCP. But principles here are the same also for slabs. It's not different. After compaction, it's best to have a hand float finishing, so behind the vibrating screed to have a nicely closed surface. For larger roundabouts, it's possible to use the slip-form paver. You see here the slip-form paver. This is the machine which sprays the setting retarder for exposed aggregate concrete, which is following. There you see the construction joint. In this case, yeah, there is no reinforcement, so it is in jointed slabs. Now there is a bit of discussion. Which should be the radius from which you can use a slip-form paver, yes or no? Do you have to impose the use of a slip-form paver or allow manual paving? Well, we have stopped the discussion in Belgium and we leave the choice up to the contractor now. Because sometimes, even for a small one, there was one who wanted to use this slip-form paver, and some of them prefer to do it even for the larger ones with a vibrating screed. Well, we leave them the choice. For a slip-form paver, mostly it's better to build the curbs and gutters, so the linear elements afterwards, so like you see here. There's just one problem. If you do it in one phase, the paver drives around, it ends, and then it's stuck. It can't be moved anymore. You have to clean it above the fresh concrete, so that is a bit tricky. You have to take care of that. And it stays there for 1-2 days on the hardened concrete until you can remove it, the machine. Or what you could do is start with a manual paving of one segment, let it harden, and then pave the rest, and then the machine can leave. But that also adds a few days to the construction process. In the Netherlands, they don't use the slip-form pavers. They have a kind of a roller finisher. As you can see here, articulated beam, and here you have the roller that moves in transverse direction and where 2 poker vibrators are attached for compaction. I've only the pictures, I've never seen it in practice. The supply of the concrete, you have to take care of a good access so that you can supply the concrete in front of the paver of the vibrating screed. For a large roundabout, it can be useful to do the supply from the interior part of the roundabout. Of course, that is not possible for a small roundabout. Yeah, in a single operation, then you have to close it, so it's always best to have a footbridge here. If the volume is too large, we say about over 150 cubic meter, maybe it's better to do it in 2 days and add a construction joint. But that is mostly something we also leave up to the contractor, or you can discuss that. But very often it has to be done in 2 operations, mainly for traffic management reasons. Then you need to have this extra construction joint, as Anne already said. And it's always best then to have the construction joint to coincide with a traffic island here in this case. You see the 2 faces. And if it's in CRCP, also in this case, to prevent too much reinforcement at the same place, you have a staggered splicing of the reinforcement bars. Here you see another example of a phased construction, lane by lane, as I said, with a slip-form paver. First, they concreted the outer lane and afterwards the inner lane. Coming back to avoiding those acute angles, we said, okay, instead of continuing the concreting, well, we add this little triangle, and that is, in this case, it is easy to do it with the manual paving and the fixed formwork. If it's with a slip-form paver, it is also possible, but then you have to add the formwork right after the passage of the slip-form paver. And here you see, if it's well done, how you avoid the angle. For the approach legs, yeah, we already said it's best also to have them as either reinforced slabs, either CRCP. Both solutions are possible. There's not much difference between those 2 solutions. It's the zone where the heavy vehicles start braking. And as I said, the best solution for me is to connect the approach legs with tie bars to the roundabout, as you can see here with those tie bars. This is exceptionally, this is a connection with dowels. It's not impossible, and this is a special case where you have the roundabout, the approach leg, and in between you have in red the cycle path in between. But of course it's not really a big issue. For the construction legs, very often we have the variable width, so you can have this vibrating screed with a variable length, which makes it easy to concrete. If you don't have, well, the vibrating screed have to pass over the curb. And finally, the protection of the fresh concrete. For a brushed finishing, best with a curing compound. For exposed aggregate concrete, we mainly do it with a plastic sheet. Plastic sheet is not so good for a brushed concrete because you're going to may have an impact on the fresh texture. So those are the main topics related to construction, and Anne will continue with the concrete mix.
It's nice to move around a bit. So what I will tell you about the concrete mix is mainly the experience we have from Belgium. So what we are using, how we are prescribing our concrete, so what we are asking from our concrete. But of course you can translate that to the concrete you have here and to the habits you have here. So what are the requirements? Of course the concrete has to withstand heavy traffic. Climate conditions are here also. You have high temperatures, low temperatures, a lot of snow. In Belgium we go a lot around zero during our winter time, so above zero, beneath zero, which is very bad for concrete. The transition around zero is very bad. It would be better to have -15 all the time than go up and down the point of zero. But so it has to withstand the frost and especially the de-icing salts we are using a lot. Also during execution, it's placed continuously most of the time. It should be placed continuously with a slip-form paper for sure. So it has to have a good consistency that it can be placed by slip-form paper. Never use a concrete which is placed by slip-form paper to be placed by hand by adding water, because then you really have a problem. So you should adapt your concrete if you have to place it by hand or by slip-form paper. You can adapt it by adding plasticizer. You cannot adapt it by adding water, because that you will see, the first winter you get, you will see the results. So don't do that. I heard yesterday, concrete, there are stones, sand, water, bit of cement, and some admixtures, and that's it. It's very easy. Everybody at home to put some tiles in the garden, whatever. I can assure you it's much more than that. You are at the high level of concrete application, so you need to take care of your concrete, especially with slip-form paper, also manually placed. If you want to have a durable concrete, you need to take care of your composition. Of course, it consists of water, aggregates, cement, and some admixtures, so that stays, but the amounts are very important, and the quality of those materials are also very important. To check your quality of your base material. Make sure, for example, that your aggregates are well graded, so don't put one aggregate 0.20 millimeter, put them in different phases so that you are sure that you follow your curve of your aggregates that you want to have. Give special attention to the sand, because sand is a really important element of your concrete. It can take a lot of water to make it workable, but that water will be released once it's in place, so it will play on your water amount. Don't put too much sand. We say around 600 kilo for 0.20 millimeter aggregate curve. But be sure that the quality of your sand is high enough. So here you see a grading of your sand which we want to have. When you look at here, the fines, so 63 millimeter, we don't like them because they take a lot of water, and you will, your workability will be very difficult when you have a lot of fines. More than 30%, between 0.25 and 0.5. We use natural sand because it's a round sand, so it will help in your workability of your concrete. And then less than 15 or even 10% above 2 millimeters, so we don't want it to be too coarse because then it will not help for your workability, and it will give other problems. So this sand is really important. If you put it by slip-form paver, don't put too much. I will talk a bit later about pumped concrete. So when you have to pump it, it's different. Then you need other workabilities. But normally we use a slump of S1, so very low slump, some millimeters, very, very low slump for slip-form paver. So the sand content is also really important. The demands on the aggregates, so we normally put our roundabouts and even our pavements, now we're starting to put them in 2 layers, but before we always put them in 1 layer. So you need a good skid resistance, and to get that you need a good polished stone value of your aggregates, especially your large aggregates. If you don't have that, it depends on speed. If the speed is not too high, you will have no problems. If you have high speed, you can have a problem of skid resistance. We had some cases where limestone with low PSV was used, and the roundabouts didn't have any problem until there was some guys on motorbikes who just thought of going to go around. It was kind of a track they could follow, so they took the roundabout, they went on a straight line again, and they took the following roundabout, and they went out of the curb. Of course, the speed was much higher than they could normally drive on it, but it caused a problem. So if you work in 2 layers, it could be interesting to have a good quality aggregate at the top layer. Just to show you the test we use for that, it's a very difficult test because you need a certain amount of stones in that way, a certain amount of stones in that way, so you really have to pick out your stones and then you test them on abrasion. Perhaps just to go back, we have other demands on so resistance to fragmentation and to wear. So Los Angeles and Micro Duval, we also have demands which are of course increasing when you go to the top layer or to a higher quality or a higher trafficked road. Coming to the cement, in Belgium we only use 2 cement types for the roads, SEM 1 42.5, SEM 3 A 42.5. We don't use SEM 2, we don't use SEM 5, we stick to those. Why? We have very good experience with these type of cements because they have a good resistance against those de-icing salts, so that really works. The SEM 3A 42.5 is a bit slower, but it works perfectly. It has a bit less shrinkage, so it's a very good, it's cement we use the most for the moment in Belgium for the roads. One thing we always ask is that they are low alkali. So we see when we use the LA cement, we don't have any problem with alkali silica reaction. So it's a good prevention method to avoid that type of reaction you don't want, because you cannot do anything against that once it's starting, and then it's very, very bad for your concrete, of course. We don't use SEM 3B. They do that in the Netherlands. They always ask me, how come you don't have in Belgium not so many problems with freezing and de-icing salts? And then I tell them, okay, we use SEM 3A. SEM 3A doesn't give a problem for freezing. We saw that when you add more slags, you get some problem with the fragmentation due by the de-icing salts and the freezing thawing cycles. We follow the European standard 206, but we don't prescribe following the 206. So we ask more cement, a lower water cement ratio in some cases, and we normally ask some air entrainer. So we have an air content from 5 to 5% minimum. In the balloon part, they put a maximum on it. In the Flemish part, they don't. We just have the minimum demand. Why? Because of course, if you put more air in it, your strength is reducing. So your maximum is determined by your strength minimum you have to attain. So it's not necessary to put the maximum. What you see here, so we make a division between the different types of traffic, réseau 1, 2, et 3. So 1, 2, 3, it means that's the most trafficked pavements, so highways, very heavy traffic pavements. These are really the local pavements where very little traffic is going onto it. We make also a difference in maximum caliber of our aggregates. Most of the time we use 20 millimeter, because then we get good noise reduction if we expose the aggregates. And it's still a very good concrete, so has a very good resistance. The 6 millimeter, 6.3 millimeter is used for upper layer. So if you work in 2 layers, we use a 6.3 millimeter for the upper layer. You see the cement content is increasing in the last case because you have more mortar. You need to have a better resistance against those de-icing salts, and that's why we increase the cement content. Together, it's not here, but in Flanders, I show you here, we go here, you see that we've reduced the water content, water-cement ratio. We did not reduce the water content on itself, because if you increase the cement, of course, your actual amount of water will increase also if you use the same water-cement ratio. So we want at least 180 liter of water in our concrete. Of course, if you have 425 kilos, you will get that 180 with 0.42 as a water-cement ratio. Why do we need that 180 liter? That is because we want a workable concrete. You can go lower. Sometimes we see compositions with 160, 150 liter of water, but then you will have a lot of problems with your workability. So you will have to add a lot of plasticizer, super plasticizer, and the addition of super plasticizer often cause problems. So especially the new types of super plasticizer, we see that there were some really difficulties with them. So we want that combination with air, so we want a composition where air entrainer is added. If you add with that the super plasticizer, it can give very weird results. You can get very high air content, which you don't want, of course. So that's why we stick to that 180 liter. Don't go much lower, because it will cause you problems. You will have problems of laying concrete and putting it in place. 180 liters is good content of water, and it will give you workability as well as durability. So that's why we reduced, at least in Flanders, and in Walloon part it will come, I think, but we reduced the water-cement ratio for the higher cement content to 0.42. The same you see here for the less trafficked roads. You see a bit lower cement content, but here you go from to 400, then you pass the 180 liters if you stick to 0.50, so we reduce it to 0.45 to have again that 180 liters more or less. I told you about the air content. I just go back once. You see it here, the minimum 3 or 5% depending on your aggregate size. In Flanders we changed. Our prescriptions are now more related to the behavior of the concrete, not to the composition. So we said, okay, we leave the air content free to the concrete manufacturer. So he has to declare a certain amount of air, and then on site we check that he has that minimum amount of air. So the L is the amount he declared, and we measure on site, and he can go minimum L, minimum amount of air he declared, and then L plus 3 as a maximum on site. That gives him some freedom to add a bit more to be sure he has the 3% or the L on site. And we are sure that the L gives enough resistance to the de-icing salts to get a good concrete, because before the construction site starts, he has to make a whole study, has to certify his concrete, and he has to do a test on de-icing salts, so to be sure that it is a resistant or a good concrete which resists to the de-icing salts. Of course, we have strength demands. That's something you can check easily. We do it on course on site. We have a demand of 70, 60 or 50 megapascal measured on course after 90 days. If you have entrained air, of course, your strength will diminish. And again, so the L is the L declared by the manufacturer of the concrete. So the strength is reduced to 60, 50 or 40 as a minimum, or, for example, 62.5 if you have 3% of air declared. For the top layer, we always ask 50 megapascal. If there is air or not, doesn't matter. most of the time there has to be air, so 50 megapascal is what we ask after 28 days. You can kind of compare that to the concrete prescribed in the EN 206. You can say, for example, this is more with air, the C30-37, so the lower strength, and then you go up to C35, 45, or even C45, 55 in the case of the highest trafficked roads without air. So that are the three classes we use in Belgium. Why emphasis on the air content? Because I think it's one of the main factors who will make sure that your concrete resists de-icing salts. You can have a very compact concrete with large aggregates, mortar content, then it will resist on itself. If you reduce the aggregate size, you have more mortar, and then you will have a higher risk on scaling at the surface. That's why we put the air in. The air are very small air bubbles we put in. You can check that very easily on site on the fresh concrete or at the exit of the concrete plant. So by the method with varying pressure, you need a vibration table, you need a calibrated air measurement machine, and then you just see the amount of air which is in your concrete. It's an easy test. In the States, they do it on every concrete batch. We do it, unfortunately, much too few times because if you don't check it and afterwards you have a problem, it is very difficult to determine the air content which was in the concrete. So afterwards, it's very difficult to say, okay, the air content was not good. At that moment, you can directly see it is good or it's not good, and the advantage is that you can tell the concrete plant, okay, the air content is not sufficient, you need to add more air entrainer, or it is too high, you need to reduce it. So you have a very good control on your concrete quality. Of course, there is that influence on the compressive strength that you see here. So if you measure too high air content, you know that you will have a lower strength. The concrete on itself will still be durable because you have that high air content, but your strength will be reduced a bit. We also use a water absorption test where you measure your water absorption by immersion, total immersion. Of course, if you have more air in it, it will appear to be higher because the amount of water you suck in is the same, but your weight is a bit lower. So this is a normal relation you have between the air content and the water absorption. We use it as a simple test to check that you have a kind of resistance to de-icing salts. It works for concrete without air entrainer. With air entrainer, it gives some dual results. It can give wrong results. It can show that you can have the feeling that it's not resistant, but it is resistant. So that duality is one of the reasons we put more emphasis on the real testing of the resistance against abrasion with the icing salts. So now we put that as an obliged test in pre-study, so a study the concrete manufacturer has to do before he can bring the concrete to a road work. We used to use the test ISO-10, which is 30 cycles with de-icing salts on it, going from +20 to -20. But now we shifted to the slab test, which is a European test. We changed a bit of the testing method because it's not always clear in the EN 12399. It's not always that easy to understand really. So we changed a bit of the testing method, but we come to good results. So what we ask is after 28 cycles, we ask a maximum loss of 1.5 kilo per square meter or 3 kilo per square meter for the lower trafficked roads. And we see that our concrete is really very well resisting, at least if you follow the rules. Again, this is a cycling path, no problem at all, till you come to the sewer inspection pit. Here, of course, this is placed after the slip-form paver went over. So they took out the concrete, they replaced it by hand. The concrete made for slip-form pavers, so they added some water to get it well in place, and they tapped very well. It means that the surface has much more water, and you see it immediately after the first winter. The surface is scaled away, so you have a real problem of scaling. So use a good concrete for the application, the way of putting it in place. If you have this case, put some hydrophobic material on it, and in that way you will protect your concrete. What is important to avoid frost damage, cement content, of course. Water-cement ratio, don't go too high, but again, don't go too low. The air content, I think it's one of the parameters you have to check on site to be sure that the concrete is good. And then, of course, the size of aggregate with the adjacent composition. Execution, so manual placed. Be sure you have the good concrete, protect it afterwards. We oblige it now in our prescriptions, so then you have a low risk on scaling. Again, an example, everything placed with a slip-form paving, even here the gutter, but this had to be closed. It is done manually afterwards, and you see the difference in resisting against the icing salts. Protection of the fresh concrete is also very important. Be sure that your curing product is not on the trees beside it. It's really on your concrete, also on the sides of your concrete. If you have an exposed aggregate concrete, you cover it first with a retarder and then with a plastic sheet. Of course, that's very good protection. If you don't make a wind tunnel, so be sure you have the ballast at the site, otherwise you create a wind tunnel and that could cause some other problems. After you removed it, after you brushed out your paste at the top of your concrete, be sure you put a curing product on top of it, because you need to protect for at least 72 hours. European standard is asking for much more days to protect it, so you need to protect it after you remove the top layer. How do you measure it? Fresh concrete, especially the air content, is very important, if you haven't trained air, of course. And then the hardened concrete, you can get some ideas with the compressive strength, water absorption, and if the water absorption is not okay, you can test your resistance to the icing salts. That's how we do it now. That test will come in advance from now on, so we know in advance that it will resist. I told you about the hydrophobic surface protection. This is what it does. So you have a concrete which did not resist. So these are different types of de-icing salts for use on airfields. And you see that there's very low resistance to those de-icing salts, or at least to those two. With the application of a hydrophobic product at the surface, so after hydrophobic treatment, you see that there is a very good resistance against those de-icing salts. So it's actually pushing the water out, it's pushing the salt out, so you don't have any problem with de-icing. The only thing is how long does it last? I think it really lasts for a long time. We also have experience with that even after some, several 20 years or so, it's still working because it goes in the pores. It will be gone at the surface, but you especially need it in the pores, and there it could be active for a long time. I don't sign for that, but we have some experience which shows that it really keeps on working. Something else is if you have to pump your concrete, if you are in urban environment, which is not really the case, I think, here, so they could do it differently here, but they choose for pumped concrete. Of course, then your composition has to be different. Your amount of sand will be a bit higher. You need a different workability, so there you need really to take care about composition. I don't think air and trainer is a good solution here, because you have the problem with the superplasticizer that it can really interact. So I would advise to protect it afterwards by a hydrophobic treatment if needed, or to test it in advance to be sure that it resists the de-icing salts. So you see for sure that the pumping it's good, but still you need a good compaction. Don't just pump it and spread it. Make sure that it's well compacted, that you have the very good concrete which resists traffic and environmental conditions. I talked a bit about surface finishing. So mainly the roundabouts are finished with a transverse brushing. It's a very good way of finishing it because you have a good skid resistance. Noise is not really an issue here because you have much more noise by braking and accelerating of the trucks, for example. The speed is not that high, so a rolling noise will not be that important. It will mainly be the engine noise. And it will last normally when you have good concrete, it will last for a long time. You can also go for exposed aggregate concrete. So in that case, you have to cover it with a retarder. So you prevent that the upper layer of your cement will hydrate. After, let's say, 24 hours, more or less, the upper layer will be brushed away. Best way to do it, I think, is with water. Could be under pressure or just by brushing with water. So you brush it away, and in that way the stones, so the small stones, will come at the surface. You need a bit to adapt your composition to have a certain amount of, so the stones between the small stones have to be there to be sure that those will become at the surface. And you can play with colors. Of course, if you have colored stones, you will have different aspects in your pavement. That's something perhaps you can invite look for it next time, because he's really expert in all colored aggregate, exposed aggregate concrete. So there are a lot of different possibilities, especially if you go to urban environments. It can give a very good influence on this aesthetical view. Coming to some special applications, I would say for the specialists between you, a turbo roundabout. I think it's a very, very good invention, because when you come at a roundabout and you have a 2-lane roundabout, you have the 2 cars coming from there, you have 2 cars there, you have to watch that car which goes to the left or to the right. So it's very difficult once you have more lanes to get onto the roundabout and to get off the roundabout. And that's solved by a turbo roundabout. Really important to get a turbo roundabout is this. So prior to the roundabout, you have to choose where to go. Or you go straight, or you go to the right, or you go straight, or to the left. So you have to choose your lane. And this is from the Netherlands, I think, because they do that there. Here they have a curb. So once you're in your lane, you cannot go to the right anymore. You're not allowed, but you cannot do it. You have to cross this. So you have to go straight or to the left. The same here. Or you go to the right, or you go straight. So you cannot go to the left. Which means that when you have to come here, so this is the main road. When the main road comes on your roundabout, there's only one car who can be here. That's the car who wants to go left, who comes from here or from there, but who wants to go to there. So here that car can choose again. If he wants to keep on going, he can do it, but normally he goes here to the right or there to the straight on. So this is really important. Before prior to your roundabout, you have to make the choice. And then your roundabout can be made like this, or just by signals, you can say where the driver has to go. Can also be constructed in different phases. We have some in Belgium, and they're very efficient for the going through. You can go further. This is advanced material, I would say, double lane turbo roundabout. So I invite you to make your choice here. Normally it should be easy, it should be well indicated. And once you make your choice, you're not able to do it differently. So here, for example, you're only allowed to go straight, and you go here straight on. Here you can go to the left, and here you can go to the right. So it's kind of double turbo rotunda roundabouts. Complicated, but once you make your choice, you're on the good road and you're where you want to be, or you're not, and then you have to make a big turn to get back. So I go further, some magic material. It's also called the magic roundabout, just to show you that you have different types. I wouldn't advise it. It's from 1972, so it's there a long time. But you need a lot of signs to make sure that people understand, especially here, it's in England, so they turn a different way. But yeah, you can keep on turning actually, so it's very strange, and I never went there. I want to go there once, but who wants can have some magic. I found some other examples. I don't see the use of this one, but it looks nice from the air, so I just wanted to show you. So now I give the word to Luc again for some examples from the different countries.
I think we're running a bit out of time, so I'm going to go fast through a few final examples. First, from our country, Belgium, we have a lot of them, just to show that the roundabout, it's not always round, it can be also egg-shaped with different axes, as you can see here. This is in jointed concrete. Sizes, you have them in big and small. This is in an urban area. It's a red-colored exposed aggregate concrete, so it's aesthetical, but nevertheless, it has been built in CRCP, even though it was a small one, so we can have all kind of combinations. This is a very special one, built in Scherpenheuvel, where you have a pilgrim place, and here they build it in a star shape, also in exposed aggregate concrete with different colors. You see more in a black and a green color, so you have the 7 points of the star. A recent one, this is the typical use of concrete. This is an access road to an industrial area where you see everything is in concrete, the safety barriers, the curbs, the central island, the pavement and exposed aggregate, and also obviously the roundabout, and with the rules as I have explained them. In the Netherlands, they have followed our example, so they also built most of them in CRCP, and this is a kind of a very large turbo roundabout in Eindhoven, a very beautiful one with the lighting. You see a diameter of almost 100 meters, 2 lanes in CRCP. And as Anne explained, they make those curbs to prevent you to go from one lane to another. Here they integrated those curbs and also put integrated lighting in the concrete. So a very good example. This is one I discovered last week only. A roundabout they call the Dream, Droom in Dutch. And also you see the cobblestones here and printed concrete. And it was a special one because they showed off with the cradle-to-cradle aspects in the low CO2 cement they used, and the special curing and rope markings and so on. But after all, it's a normal roundabout. But this is a special one because that is the first time I saw it. It's also in the Netherlands. Well, they built 2 roundabouts, and one of them, they couldn't put it in place directly, so they built it at one place, 50 centimeters thick, and they moved it over 60 meters to put it in its final place. So it was, let's say, precast on site and then moved into its place. So that was very special. I never heard about that. And even more precast, as you can see, is this, and that's also only a few weeks old in the Netherlands, where they composed it completely of precast elements, both the inner and the outer circle, and then put everything together in place. You see so many possibilities. In France, they also have a lot of them. You see our colleagues from Simbeton, they have a publication, T56 on it, with 11 examples, several types of construction, also both GPCP, CRCP, and some of them with thin concrete pavements, only 10 centimeter thick. I'm not that fond of that. I think if you build a concrete roundabout, you better build it in a robust way. But anyhow, just to show that it is possible. In Europe, I already showed you before examples of in Austria and in Switzerland. There are a lot of roundabouts. In the United States, I told you about the one that we saw, one of the few in Wisconsin. You also see here the adapted signing, because the Americans, they are not really used to roundabouts, so that they know how to use it. And as I said, it was a doweled one, transverse brushed, and also with crossing places in imprinted concrete and with the matching joints. So it's a nice example. In Australia, they had that guide in 1996. I was there in 2011 with a group of American people, and they also used the isolation joint, but you see some deterioration of the joint. They use steel fiber reinforced concrete. You see here a lot of steel fibers on the surface, and no surprise because they use up to 80 kilograms per cubic meter, which is a very high dosage. And that's why they say they don't use any dowels, because they say, oh, we have a lot of steel fibers, so we do have the load transfer. However, I saw that there was some faulting, so there was some steps at the joints, so I don't think that the load transfer was that efficient. So, ladies and gentlemen, that brings us to our conclusions. I think, yeah, concrete roundabouts are a good solution, both in terms of strength, especially for the intense and heavy traffic. We have a lot of different solutions, both technical, aesthetical. They can be built fast, and you can later on ask us questions, but please don't ask us any questions about maintenance, because we don't have any experience with maintenance of concrete. So the roundabouts,
nor to the government, the administration.
They
don't
require a good preliminary design and a careful execution, and then you can come to a good success. All what we have told, of most of it, is in our UPAVE publication on concrete roundabouts, but I'm very happy to see that most of it has been translated in a very fine brochure. Thank you, Francie, for your help to that. It's really great, so you have all the details here. And I end with this picture. This is a special one. It's a nice roundabout. It's only 50 meters from the place where I grew up, from the home for my parents. So, and it gives you all the details that we explained, and you see all the road users which are possible are on the picture. So, ladies and gentlemen, Anne and I, thank you for your kind attention.